Hello everybody. I'm going to present our online short video for JSS Happy Hour, take place at the end of the May. So I have been asked to present this particular paper of ours, which has been published in JSS recently. Essentially, this was a great joint work with 4 other colleagues. So the 5 of us conducted a meta-analysis of how to align software engineering education with industrial needs. So I'm going to present a few slides, just a very few slides on this topic. So in terms of very brief outline, I will have one slide about the context and need for this study, and then the research method and our review questions, and the results and their implications and benefits. So really, we have there's a tremendous need for expert and high-quality software engineers and graduates. So this is actually from the Medium website. A practitioner mentioned that it's quality, not just quantity. So we need more software engineers with top skills. And so in this kind of 3 photos that I've placed here, this is actually, so the first phase is really study software engineering in universities, graduate from university, and then work in the software industry. This is actually a photo from my own students where I was teaching software engineering course in the University of Calgary in Canada. So it's really the quality of software engineering workforce is a direct result of the quality of the education that we provide in the university. So as educators, we have to do our best to make sure what we cover is aligned with industrial needs. To address this need, actually, many papers have been published in the last 20 or more than 25 years, I would say. So about 35 papers, according to our literature review, that have focused on the issue of aligning software education with industrial needs. So our search criteria was to find papers that just focused on this very topic. Of course, there are many, many papers in software education, but we just wanted those that talk about aligning, how to align them. And most of those studies have been gathered data, mostly using opinion surveys in regional and limited regions. So it's really the motivation for this study, for this meta-analysis, has been that we really need to synthesize and aggregate data from all those studies into one consolidated view. So we raised many review and research questions. The main two ones were importance and usefulness of software engineering skills, and then knowledge gaps, deficiencies. So we used the SUIBOC Software Engineering Body of Knowledge version 3, published in 2014, which had 13 knowledge areas. I'm going to mention some details. We had 8 research questions in total, but in this short video, I will just focus on these 2. So we gathered through a systematic search process 35 papers in total. As you can see, the annual chart can be seen here. The first paper that we had in our pool was from 1995, and then we have had more papers most recently in the last 10 years or so, 15 years. For example, 4 of the papers under study are shown here. The first one is by Mr. Lethbridge. I actually know him, he's in Canada. Survey of the relevance of computer science and software in education, published in 1998, and a few other example papers I'm showing from our pool. In terms of our data set, we gathered the countries that these studies have been conducted. So really, most were US-based studies. There were essentially 4 papers in Canada, collected data in Canada, South Africa, New Zealand, etc. Histogram of the number of data points. So we were wondering how many data points, how many participants each of those opinion surveys had. So this shows that many studies had slightly less than 200 or 250 participants. Few studies had more than around 500 participants, as you can see, 560. So this is number 1 here. This is a histogram. When we added up all those number of participants from all those 35 studies, the total we got was 4,132. So this shows that our study provides the most comprehensive view on the topic based on the empirical data points. You may ask, how did we gather data? the numerical and quantitative data to assess importance and usefulness of software engineering skills. I'm going to show you an example. Here, essentially, I'm showing, we are seeing one of those 35 papers. This is kind of the screenshot of the PDF. We look at the paper, we find where it presents the list of most and least useful software engineering topics. For example, there's general architecture. This is actually the most useful towards least useful. So we look at the rank of them. And for example, architecture refers to design and architecture, SUI bucket area. Object-oriented analysis is also in the same topic. User interface design also is design. So we say 1, 9, 12. We get their average divided by 13. 13 is because I have 13 knowledge areas. So this gives us a number between 0 and 1, which is the normalized importance or usefulness metric of each area. Remember, we put all this data together, we get a nice chart like this. This is a scatter plot showing the importance of software engineering skills. We look at number of papers each topic appeared into. You are seeing 13 knowledge areas of SUI here, and the y-axis is the importance metric that we got from the previous analysis. Here, essentially, well, for us, like these two things were important. We can have a topic which appears in more papers that could be seen as a proxy of importance, and then actual importance data. So the more data points we have on the kind of top right, they are very important. So we have design, testing, development, project management. And software, so it's surprising that topics such as software engineering economics is seen this importance, and then you have math foundations. It means that perhaps we don't have to teach too much math and on other things. What we can see is that, for example, testing, design, and requirements are very important because they're on the top right-hand side. For research question 4, knowledge gaps, we also have the details of how we extracted this data. But again, this is scatter plot, shows the data, the final results. On the x-axis, we have average importance, so between 0 and 1, and average knowledge gap. So this gives us a nice quadrant system here. In Q1, we have high importance and high knowledge gap. Low importance, high gap. Low importance, low gap. High importance and low gap. So this is kind of, these two are especially very important. This topic, and we see lots of points there: testing, design, software quality, software engineering professional practice, project management, process topics, configuration management. This means that these areas are very important in the industry, and unfortunately, in the knowledge that on average those 4,000 respondents mentioned statistically, they felt that they had slightly high knowledge gap comparing what they needed to know in industry versus what they had learned in academia and universities. This is slightly mentions a slight shortcoming or deficiency of our software engineering education, to be honest. So that is what really the empirical data are telling us. So topics in Q1 are those which need the highest attention from educators and needs for improvement in university programs. So that's the end of my very short talk. We looked at the needs of the study, research methods, and their questions, and some of the results. I am looking forward to more questions and answers and conversations during the happy hour, JSS happy hour on May 29th. Take care.